Hi, music lovers. This is Dorian, also known as a great white bird. That's my ambient composition name. And I'm here to explain something it took me a while to figure out about sound. It's like the most basic thing about how notes and frequency and wavelength work, how they interrelate. I used to wonder, what is an octave? Is an octave some kind of thing that people just invented because it sounds nice? Or is there a reason why it sounds nice? Is there a reason why it sounds natural? And is there a reason that, the other intervals that we use in music sound the way that they sound? And the answer is yes. And the relationship is really pretty simple. And it's pretty obvious and it's kind of cool. So I just wanted to put it together in a way that made sense. So I'm going to put it together using my keyboard here, this little ghetto keyboard that I have, and Audacity software, where I have plotted out these three notes for demonstration purposes. So the notes that I'm plotting out just to demonstrate this are C3, G3, and middle C, which is also known as C4. So that's that note. So any piano you go to, this is going to be the in the middle of the piano or whatever, or it'll be this. And then so this note here at the bottom is the high one that I'm using. That's C3, and then this is sorry, that's C4, and then this is G3, the note that kind of, on a keyboard it's right between those three, but it's not right between those three in terms of wavelength and stuff like that, because wavelength and notes have this relationship that is logarithmic. It's a logarithm. And if you don't know what a logarithm is, then hopefully by the end of this you will know. And so anyway, that's the bottom note, C3, that we're demonstrating. So a logarithm is where, like for example, on the Richter scale with earthquakes, like you get a 2.0 earthquake. Well, a 3.0 earthquake is actually twice as intense as a 2.0 earthquake. And then a 4.0 earthquake is twice as intense as a 3.0 earthquake. That's exactly how octaves work. So this, this C3 note makes a wavelength that is half the, or it's twice as long, and it has half the frequency as the C4 wavelength. So to give you and what a wavelength is it's just it's the distance between like that, like it's that distance, or it's that distance, or whatever. And what a wavelength is like if you see a speaker vibrating, it's pulsing in and out. That's what it's doing. It's just following this path that a signal gives to it. And the reason that that turns into sound is because it makes this like wave in the air. It's a vibration that comes through the air, and it's just like an ocean wave, except it's so fast that it becomes a vibration. It's not a pulse, it's not a movement. It turns into a sound. And this is the same thing. If something gets way faster than sound, it turns into something else. And if it gets way faster than that, it turns into light or whatever. The universe is expressed in wavelengths along the whole electromagnetic spectrum. And so sound is underneath the electromagnetic spectrum, or I don't know, it's the lower part of it or something like that. And your heart beats real slowly. The beat of most music, happens real slow. It's like boom, 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 boom. But if you increase that to the point where it was too fast, any drum beat would just turn into a tone. It'd be like, right? It would turn into something. So the reason that these different notes sound the way that they do is because of this cool relationship that exists between their frequencies. So I just zoomed in a bit. Don't get too don't get too, you know, flipped out over my zooming. So here's the, here's the C4 note. That's this, right? That's that. And you can see every time a C3 note goes through one oscillation or one wavelength, the C4 note that is one octave above it goes through two, and the C5 note that is another octave above it, which I'm not showing here, goes through four. And that's how notes work, and that's why they sound the way that they do. So that's how an octave works. And everything, all the relationships between the octave sound the way that they do because of the relationship between those frequencies. Just as a little bit of coolness, that sound wave is about as long as I am tall. Okay, it's longer. It's like about 2.5 meters, 2.6 or something like that. So that means that this sound is about 1 meter long. So that means if this were actually to scale, like if this was, view at 100%, if music programs did it that way, then this would be 1 meter long. And that's how sound waves work. So let's say if you want to cut out a sound wave that is at this level, you want to cut it out completely, you want to soundproof it completely, you've got to have a wall that's 1 meter thick. Anyway, so the relationship between these two waves, these two, notice how cool that sounds. Any musician knows, that's a pleasant sounding frequency, whatever, that sounds the way that it sounds because it sounds cool. So I'm going to try and zoom out here. So the reason that it sounds that way is, let's see, these sound waves, the lower one, the C3 one, and the G3 one, they meet up after G3 goes through 3 oscillations and C3 goes through 2. So that's where they meet up, right? And then it's basically the same like when G3 goes through 3 oscillations, C4 has gone through 4. So the simpler the fraction is, or the whatever, this is 3 to 2, and this is 4 to 3. And the simpler that number is, the simpler the fraction is, the more like comfortable the sound is. So if you have some interval like this one, the reason that it just sounds less simple is because the number is less simple. Because this note has to go through a bunch of, I don't know what the relationship is, but it's a silly sounding fraction. It's like, 15/9 or something like that. It's a crazy relationship. It's not as simple of a number as 3 and 2 or 3 and 4. And it sounds more complicated. It sounds different. And it's because it's, this is just another way of saying this. It's like a similar kind of relationship. So that's why this sounds the way it does. This sounds the way it does. That sounds the way it does. And that is the basics of like why chords sound the way that they do, and how like musical notes relate to wavelength, and how musical notes and octaves proceed up the frequency range. And that's how that works. Yay! Music is so fun and strange.